So I think it's recording. Switch over to the whiteboard. All right. Okay. So we are recording, I believe. So we're gonna start the class for today. Um, are there any questions, I guess, before I begin? Okay, good. So what was the last topic that we looked at last week? Looked at history. Oh, that's right. So we did the history. Yeah. Oh, yeah. What were we? Okay. So did we finish the XOR? We did, right? And that's your homework assignment. So you all have done that. We deployed it on Thursday, correct? So we deployed the XOR. So basically that's all online. You can just go and, replicate the results. So today then, we are starting, this something very interesting. You are now going to learn how neural networks learn, right? So you know about the weights and you have this intuition, but you're going, and I talked about a lot of the people in the history. So we're going to start with that. We're going to start with the first one, which is called the perceptron. Okay. So we're going to code it up basically. Yeah. So that's the one I mentioned. Yeah. So we're going to go over the perceptron. Okay. So this is what we're going to learn today. And basically, it's going to be actually in NumPy. So it's not even going to be in TensorFlow, right? So a lot of what I'm going to try to do is, whenever possible, we're going to code up the neural net in just NumPy just to really understand how everything works. And then, of course, we're going to be switching over to TensorFlow as well, okay? So that's the basic idea. So you remember the history of the perceptron. So I said what? That it was implemented for the first time by Rosenblatt, I believe, right? And so they made it available. And so, that's what we want to understand kind of this week, right? We want to go over the code and see how it works. But what's so great about neural networks is that they actually they all follow the same ideas, right? So I always say that you understand the perceptron and you understand already 60% of deep learning, right? Of the things that we're going to cover in the class. We're going to explore some interesting ideas. There's been a lot of little things that they do to neural networks for them to work better and better. So it's always like an incremental kind of a thing. Okay, so basically then the perceptron, this is going to be an example, and it's going to be a binary classifier. So we've seen binary classifiers before, okay? And the idea is that it can predict either -1 or +1, or it can predict 0 or 1, right? So, but it's a binary classification problem. So we're going to define some function that we want to learn, and this is basically a linear combination. Now, we already looked at this, right? I did this code some time ago. We looked at something called the dot product, and we did that in class. We wrote the code. If you remember, it was basically the mechanism that allowed us to multiply x times w. Do you remember that? And that's basically the operation that we always do, right? Is this kind of multiplication with matrices and vectors, etc. But basically, this gives us our linear sum. And it's always this, so the line equation, mx plus b, it's always this, okay? These are at least in neural networks, I should say. In neural networks, right? There's naive Bayes and other, they handle things differently. You saw that in KNN, it was also different. So we will need basically then a linear combination of certain input values and corresponding weight vectors. So this is called a linear combination. Okay. And then of x and w. the thing is, we know what the x's are going to be, but we don't know what the w's are going to be. You see that? That's the thing that we have to learn. That's the thing that makes up a model. A model is just architecture with, you know, neurons connected somehow by weights, but we don't necessarily know what these weights are initially, and that's what we have to learn. Okay, so that's going to be the idea. So we will write our function basically like this. So our notation, because we have multiple values in there, right? So we're going to have y equal w1 times x1 plus w2 times x2 dot 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 wn times xn, right? That's always the equation. Okay, where the x's are the inputs. So for instance, for Iris, it was 4 inputs, right? And then it means we need 4 weights, right? And so we need to calculate a weight for this x, a weight for this x. And so that this is called a linear combination, okay? All right, so it doesn't have, you know, something like that, which makes it non, you know, quadratic or polynomial, etc. It's always like this, okay? Makes sense? So this is basically the idea. And then we, you know, you sometimes see this notation here. So the notation of w vector x vector, which can be written, and this is the code that we actually did some time ago, where we do from I to 1 or 0 to n of xi times wi, right? But it's basically that we multiply them and then sum them, right? And we did this code, I'm pretty sure. So that's kind of review. So I'm just going to go over some of the ideas of the perceptron, and then we're going to write the code, okay? But I do want you to get a sense for what's going on. Okay, so let's go over here. Now, keep in mind that whenever we write an equation that is like that, there is the equivalent neural network implementation, right? So we always have like the formula, we always have like the graphical neural network, we always have the code that we can write, so that, but they're all kind of the same type of a representation. So the question is, how do we learn these W's? Okay, so as you might imagine, there's basically a procedure. Now, as I said in the history, the main procedure, stochastic gradient descent, was the paper in 1986 by Hinton and them. But before, in the 40s, the perceptron also had a procedure, right? It's got this procedure, and it's very similar, just simpler, a lot simpler. All right, so that's what we're going to go over this week and then implement it in the code starting today. So the question is, how do we calculate these? And these are all sometimes called the parameters, because there's always this also an implication that there's a bias. So there's always the W's and the B's. You always do this and calculate. And so basically you end up with that and that, which are called the parameters, okay? But this is the weights, this is the bias, and both of them make up the parameters, or the weights vector. So how do we do this? Well, it's actually like in a for loop, we can think of, you know, so let's think of training, right? So training, right? Learning. So first, what are the steps? So we have a neural network. These are the x's, x1, x2, x3, x4, and then these come to another neuron like that. I'm just using 4 in this case. We have got to learn these weights, W1, W2, W3, W4. And then we also have an activation function, which basically means that this goes, let's say, into another step, although usually we refer to this as just one neuron, but I'm drawing it as 2 here. And it goes, this value, let's say it's Z. So then it goes into this function, right? And then it comes out as a response, right? So there's something called an activation function as well. which we've seen already what the activation functions can be, like the sigmoid, right? We saw the sigmoid, the tangent, but actually for the perceptron, you use something called the step function. And we're going to see what that is. And then we're going to go over the algorithm and kind of get an intuition for how it learns. Okay, so what are the steps? Let's start with step number one. We have basically then the architecture, we have the X's and we have the W's. The W's are the thing that is unknown, so you have to learn them. So you have to start with something. So usually what you say is that you initialize the weights. You initialize the weights. So how many weights do we have here that we need to learn? 4, right? We have 4 weights, W1, 2, 3, 4, right? So we initialize usually like a vector or something, and we need to initialize these to some value. So what do you think we should, do you think that matters? What do you initialize them to? Why does it matter, actually? If you're sure, that's what's going to happen at the end when you learn. But why is it important to how we initialize them?
Doesn't it also help
is stabilized, maybe? Yeah, but anyone else have any ideas?
It would be different.
Different minute, and what is that? Mm-hmm. Mm-hmm. What is that? Different minimums. Where's that coming from? Where's this minimum that you just mentioned?
In
terms of error? Yeah. Yeah, so that's actually a very high concept, right, that we're going to take a look at. But to address it, so I've told you guys that this is actually not done here. I want to stress, right? The perceptron does not do this part. But what gradient descent did with Jeffrey Hinton and them is that I said that there's 2 functions actually involved later, as we will see, right? This one, in the perceptron, we have this, but we're not going to have this one. You see that? All right, so that should be this is called a cost function. And you've already seen cost functions. Like you saw this minus this squared, right? That's a quadratic function. Do you see that? But if you notice this y, let's say this is y hat, that's going to be your x and w vector plus b. So this function plugs in here. Do you see that? And then you minimize this. You minimize the cost. Because as you can see, let's say that, the difference, let's say these are the real values and these are the predicted, right? What if the differences are really big? Then the difference here is going to be a really large value. Does that intuition make sense? Whereas this is only for linear regression. Whereas once your model starts to get pretty close to the real, then what's going to happen to that error is pretty tiny. Yes? Right. Good. So later on, we're going to play this fun game, right, between the y function and the j function. Both of these work together. As I said, the j function is basically written like something like this, where these are the real values, and this is just literally whatever inference function we have plugs in here. Actually, I did say that I was going to give you an extra credit assignment. It ties into this very strongly. Okay, so it's a proof that I want you guys to look at. All right, so basically this plugs in there. Now, the important thing about this is, this thing about the mountains or the valleys is that there's a graphical representation of this, that you can view it, right? So really there's 2 graphs then, just like we have y hat and j as functions, there's also these 2 interpretations of them visually. Okay, you probably already get this one, right? We've done it before. You have the x's and you have the o's, right? and then we were trying to build a line or a curve that separates them, correct? That is the visual interpretation of the function. You're learning this function, and it's the classifier. Does that make sense? But this other function, that's j, right? So it is a function. Do you see that? Can be represented as a second chart or a second plot. Okay, and that second plot where I'm just gonna, so I'm gonna keep y here, and I'm gonna say this is the graph like that, right? For this one, the j, which you can write it as, for a simple case, this function. It's what is called a quadratic, right? This thing here. When you have a very simple network, like a linear network, something like that, it has an interpretation, which is like this. On this axis, you have the cost, j, basically. And on this axis, you have the thing that is of interest to you, which in this case would be w. Why w? Because w is the thing that is changing, the parameter. Do you guys see that? And so what happens when you're trying to learn? You pick a w, right? These are the weights. So remember, you have x, w, and so on, right? So we're just going to look at one, just one, all right? I want you to just to get the interpretation of this. So we'll have time to look at the math. So cost just means, obviously, if it goes up, it's a higher cost, right? So what do you want? You want the cost to be low, correct? So what happens then if I pick this w, let's say w1 as the weights? Well, it translates to that for that function. Who governs this function or this graph here? Who governs it? This, whatever you have in this function. Do you guys see that? Does that make sense? So let me do this. I'm going to imagine that this is like, I'm breaking this up into little pieces. So this is W8. You see that? You found W8, and governed by this function, what does this function tell you about W8? Is it better than W1 or worse? Why? Because it's a lower cost, right? Basically, what I'm saying is this thing here can basically, not that it's an analogy, it is literally happening, right? That it's this, because this is a function, right? It's a quadratic function. So in a quadratic function, can you find an optimal minimum? What is the optimal minimum here, roughly speaking? What would you say it is? Probably that one, right? So let's say that one is W4. It found the lowest, and that is the solution to the problem. So then but then this has a perfect solution. So why do you have local minimums then? You see what I'm asking? So you said about there may be multiple local minimums, right? But this representation that I've drawn actually has only one global minimum. Do you guys see that? So how do we end up with multiple local minimums? So what happens is that, yes, this is true, gives you that. But a deep neural network is a function that where this little thing is not a simple linear function. It is a deep neural network with nonlinearities. And so that component, regardless of this, makes the thing pretty complicated. Do you see what I'm saying? So that's actually the proof that you guys are going to do. I'm going to give you a little, if you do it, right? I mean, it's a bonus point. It's kind of an assignment. But I'm going to give you a scenario, and that is, it's going to be called why. What is it that I called it? why deep learning algorithms are non-convex, something like that. So I can't remember, but so I'll give you that task. But it basically gets to this, to the heart of this, that when you plug in because remember, you agree, right, that this y hat here is your neural net, correct? And you know that it can be very deep, have a lot of neurons, and it still does. And also you probably use something like logistic cross entropy or some other optimization. But really what makes the complexity is this. So then to go back to what she was saying, when it's a deep neural network, the graph no longer, unfortunately, looks like this. You see that? Instead, now it can look still the same principle. J is the cost. The W's are here. But now it can look like this. You see, it's no longer what it was before, right? Intuitively. And the neural network causes this. So now to go back to the question and the answer, why do we pick different W's randomly and several times? Because one time you might pick this W. As it turns out, gradient descent just finds the way to the lowest point. But what can happen is gradient descent will come here and then never gets out of there. You see that? And it arrives at that solution. That might be W3. But what if you try another one, another weight, and you fall here? Think of it as like parachuters coming in a mountain range, right? So this is another weight randomly picked. You see that? And you hit there. Are these the optimal solutions? No, because technically there is one that if you find like this one, let's call it W7, that would give you the lowest value. Do you see that? Now, we are really getting ahead of where I wanted to get, because that's all, first of all, this is stochastic gradient descent. That's where you need an algorithm. We need to understand how it works. As it turns out, it involves the derivatives of this function at specific points in time. So we're going to look at all of those things, right? But this would be the intuition of definitely looking at different W's. Got it, guys? Any questions? Nope. All right. So now keep in mind, though, this is for a deep learning algorithm, deep learning, and it provides that function, right? But you can simplistically think if it's not a deep neural network and it's just a simple linear function, you could end up with a quadratic function, which means it has an optimal solution. All right. Now, the perceptron does not use this because this process requires looking at the function, right, that you've written out and then doing steps to it, right? So instead, the algorithm of the perceptron is just a little bit simpler, but it still kind of works. It just doesn't work for things like XOR, right? So this is the kind of thing that I think I mentioned in the history that Minsky said, that it doesn't solve things like XOR. So let's go. So any questions about this? This is kind of a quick introduction to this. We will come back to it later. All right. So let's go over here. So basically, we were talking about the steps of the perceptron, right? So, and like I said, a lot of this translates to deep neural networks. There's just a little bit more complexity. So first of all, we initialize the weights. So initialize the weights. And weight initialization is pretty important. Usually people initialize them to random values with a normal distribution. That's kind of like standard approach. But you can initialize it to all zeros, all ones. We will play with those values. For the complexity of our networks, it usually doesn't matter. So initialize the weights to, let's say, 0. Okay, so we can initialize them to 0 or small random numbers, which is probably better, small random numbers. Then we're going to iterate through the data in a loop, right? So let's just say for each training sample, which could be in batches, by the way, but for each training sample, X, perform the following. form the following. So what do we want to do? We want to compute the output value of y. So we always predict, right? Whether we have bad weights, good weights, we always predict, right? So the first step is predict. Predict using y. So using y, x, w. Initially, the first step, the w's are basically, you don't want them to be 0, but you want them to be like small random numbers. I'll show you, I have a little graph in a sec. We're going to take a look at how the process is kind of nice. All right, so predict using this function. So we always predict. Let's call it hat, actually. That means that's the prediction. So compute the output value y. So we compute y, and then we want to have some way to compare y with the real values. Okay, so we want to have some way of comparing that, right? And then I'll write C here. Based on that comparison, what do? What makes sense to you? We update the weights. We update the weights. Okay, so that's the next step. And that's going to be the perceptron. So then we have what is called an update equation or an update rule. We have the update rule or equation, right? And that's usually the weights, each weight, I should say, plus some value, delta. This value you need to figure out, okay? And there's some tricks, but basically what's happening is initially the weights are something, right? Zeros or whatever they are, and then you're gonna add to it. Every time a little bit, and every time the weights change, you predict, right? And you keep predicting until your predictions are pretty good by using this update rule. Does that make sense? So this was the initial intuition of the perceptron. And as we will see in the code, it works, right? It's just, it wouldn't work for deep learning. And so, but at the same time, it's very similar, right? So it's just an extension of it. So how do we calculate this value? So we have a perceptron learning rule. So this is just for what was done in the 40s, the perceptron rule. Okay, which would say that delta W is basically the y minus the y hat value multiplied times an n, which we're going to change that name later to just learning rate. It's just a little value. So we decide what value we multiply it times. And then sometimes you can use the same sample values in here. Okay, although this is not necessary, we can get it to learn just like that. Okay, and that's it. That's basically all we do. So if you look, the real value minus the prediction times what is called a learning rate, just some little value that you pick, right? And then you update the weights iteratively. And the thing is, what's going to change with deep learning is how we calculate this delta W. We want to calculate it in a very efficient and fast way because otherwise it's going to be learning forever. You see what I'm saying? And so that's going to be stochastic gradient descent. So n is the learning rate here basically, which can be a constant. And that's going to be a whole bunch of different values. It depends on what you're doing. All right, so let's take an example here of how this would work. So example using the update rule. So the update rule, let's say that we have a problem. This is just a simple example, -1 and +1, right? So we have the update rule, delta W, and we have n. And let's say that the label, the real label, is what? The real label is -1, right? So then we plug in -1 minus, and then this is going to be the predicted spread, right? So then what's going to happen to the value here? This is minus 1 plus 1 becomes 0. Intuitively, it was correct, right? So there's no change to the weights. Do you guys see that? So this is like the simplest way that you can take a look at it. Make sense? All right. And then if you do y equal 1, that's going to be delta. Oops, sorry. That's going to be delta W. And that's going to be N. And that now it's real minus, predicted correctly, right? So again, 1 minus 1 equals 0. So there's no update, basically, that's happened. You guys see that? So this is the, so nothing is updated in those particular scenarios. Okay. On the other hand, if there is a value, then if it doesn't predict correctly, then there's going to be a value there. So for instance, let's say that, oops, let me go over here. Have delta W equal N, where the real value is 1, but it predicted minus 1, right? So it predicted incorrectly, correct? Because it's 1 and predicted minus 1 for this particular case. So that's 1 plus 1. So that's going to be 2n. Oops. You guys see that? Now, this is not like a perfect mechanism. It's not a perfect mechanism, but it was the perceptron's mechanism. And it did, as you will see in the code, it kind of did a job, right? It worked in a sense, right? And you can sometimes multiply it, as I said, times other values here. But we're going to ignore that. And then here, I'll just do one last. So again, the learning rate, this is important because it determines by how much you modify the weights, the original weights. So this here, we're assuming the real value is minus 1, so minus, but it predicted 1. So this is what? 1 minus 1 is minus 2, correct? N. Do you see that? And so now it's going to go down. So it goes up, goes down, and it's kind of like that, and that's the procedure. Okay, so this is important to understand because, like I said, a lot of the time we will be exploring these ideas. Okay, so that's the update rule of the perceptron. Any questions? Nope. All right. And then you need to have a value, right? That, as I said in the graph before, so this is, once we have that function, okay, so we have this function of x1, x2, x3, x4. These are the neurons. We found the weights, or we have some weights, W1, W2, W3, W4, right? And then this is the sum of them, right? You guys understand, hopefully, that this is the same as saying, so I'm going to call this Z, and this is the same as saying W1, X1 plus W2, X2 plus W3, X3 plus W4, X4. That's exactly the same representation here, but now to get the Y, we still want to run it through a function, right? We've talked about this. These are sometimes called the activation functions. And so I'm just denoting it here because this is the convention in the perceptron. And this activation function can be a lot of things, right? Can be a lot of things. In this case, it can be something called a step function. Okay, and then that becomes the output, okay? Do you see that? All right, so now let's talk about this step function a little bit of what it can be, right? So basically, it has a graphical interpretation like we've done before. right? And it's basically something like this. Now, it can be something like this, right? So this is the value that we're coming from, right? The C-axis, I guess, C, and this becomes the W, right? So it can be -1 or +1, correct? Whatever the value is, you have some rule, like if it's negative, it's a -1. If it's positive, it's a +1, right? Or we can just shift it up a little bit. Z, Y still. What's the only difference here? 0 and 1, right? Yeah, exactly. So 0 and 1, right? But it's kind of the same idea, right? So this is a step function. It's still a linear activation. Okay. All right. So that's it basically as far as the theory of the perceptron. We're going to go ahead and implement it. Now, let me ask you a question. Now, I did say in the past that whenever we have a neural net, right? Like this, X's and W's, and we have activation functions. I kind of did say that neural networks have that behavior, deep neural networks, multi-layer perceptrons. And that allows them to create functions that are nonlinear. You see that? But what about this one, the perceptron? The perceptron is running through an activation, right? So it's got this part here, but then it's running through this activation. Does that allow it then to create nonlinear functions? You know what I'm asking? So I think we did this with the XOR, right? We did this with XOR. So I said something like, and you guys had that homework of playing with the architectures. So with XOR, I said, right? And then something like that. There is no linear function that separates this, correct? That's what a linear separation is. Nonlinear means that, right? You get pretty good accuracy. I said deep neural networks do this, right? And you guys probably tested this in your homework. And then you saw that something called logistic regression does not give you this, right? It can only create lines. So the perceptron, now I ask you this question, the perceptron is a network, but it's going through an activation. So I say that the activation is this step function, right? But what if you change that activation to some other function, like a sigmoid function? Do you guys remember the sigmoid function? Looked like the little S thing. Or a ReLU. Do you guys remember that we saw ReLU and that was associated with deep learning? So my question is, if you change the activation if you take this architecture for the perceptron, but you change the activation to ReLU or sigmoid or one of those, does it make it now able to create nonlinear functions? What do you think? Why not? It's not a deep neural net. Yeah, so this is an important concept because it can be a little bit confusing, right? Anyone else want to? Yeah, so yeah, you're right. So the reason is that, and this is important to understand, the thing that gives it the nonlinearity is the layers. That's where I'm getting at. Maybe I didn't phrase it well, but yeah, that's what gives it, not the activation itself. Because then the perceptron, if you just change that last input and gave it a ReLU or something, it would also be able to create these. You see what I'm saying? You have to actually give it the layers, right? So I have a little graph for this. Let me find it. Just give me a sec here. All right, so I need to stop sharing probably. So I was already, how do I get to mine? Oh, there we go. Can you guys see this? Maybe I need to share. So I created a little thing under neural nets because this is an important concept, actually. Sometimes we kind of understand, and this ties into your XOR homework assignment. So here you can see the perceptron, right? So I provide a little bit more. I'm a big fan of the history, so there's a little bit more information here on that Marvin Minsky thing, and you can take a look at it. It's funny to read, so if you want to read it. But basically, you have this, right? This is what we're talking about today, right? The perceptron. So the question is, consider the perceptron as illustrated in the figure above, right? So you've got these activations, which are nonlinear, or sorry, linear. It can only create those lines, right? But then you have these other ones that are nonlinear. So people often refer to the, oh yeah, we added a sigmoid, a ReLU, those are nonlinearity, boom. So then a lot of the time you might say, wait a minute. What if I just put you might have this moment of revelation at home and you're like, what if I just add to the perceptron a ReLU? Does that make it nonlinear, right? So that's the question, right? So you can see that here, which is what I was saying. So consider if the activation function is linear, like the first three cases, then the perceptron is equivalent to a linear classifier. You know this, right? This is kind of what I'm saying, right? However, and you've proven this with the logistic regression that you did that couldn't really separate the data. Consider, is the perceptron equivalent to a nonlinear classifier if its activation function is sigmoid, like one of the other advanced functions that we learned? So in other words, can the perceptron represent any complex function if using a sigmoid as its activation function, right? So that's the question. You can think of it like in an exam, this would be like a trick question. I'm definitely trying to trick you. But basically the answer is, and this is the insight that you should really take and appreciate about neural nets. The network in the diagram has an input layer and an output layer, but no hidden layers, right? Input the X's, the W's, and then they just sum to that one neuron. And then that one neuron goes through the activation. Do you see that? But it's not going through intermediary hidden layers. So then this type of network can't perform nonlinear classification. It can't solve XOR basically, okay? Or implement arbitrary nonlinear functions regardless of choice of activation. So it's not just the activation is really what you should get out of this. However, and this is really important, things change radically once the network contains at least one hidden layer. That's the power. This is why, and this goes back to the universal approximation theorem that I mentioned, right? I am careful in saying at least two hidden layers because pretty much everyone says it, but technically, possibly even just one hidden layer. It changes everything radically, and then it can approximate any function. So this changes radically. Things change radically once the network contains at least one hidden layer with sigmoidal or other nonlinear activation. So this is where it's confusing sometimes, because then you might say, okay, then I just need layers. You need layers and activations. But just an activation with no hidden layer does not make a universal function approximator. You guys see that? There's a little trickiness there. But if you just make a neural net, another trick question could be if you just make a neural net with a ton of hidden layers, but they don't have activations, what is that one? Still linear. Okay, very important. All right, so this is the combination of the two. Such a network can indeed perform nonlinear classification and approximate arbitrary functions, okay, and so on. So that's kind of the idea. Got it? All right, good. One last thing I wanted to show you is kind of how the model is learning. So I have a little graph here, and then we'll just start the coding portion of today. So let me go over here. I want to show you what it's doing with the error. So if you have a stable neural network, that's your error, like pretty much in the beginning. What is that function called? It's a Gaussian function with zero mean, which basically means all errors. This is modeling the error itself. What is the error? Y minus y hat, right? So basically, the errors are Gaussian. You can check for a neural network for its stability by pretty much at epoch 1 getting this. The weights kind of give you this. And then basically over time, this will narrow. If you have an unstable network, right, what can happen is it starts like that. Do you see that? That's an unstable network. Why? It's predicting badly. Do you see that it predicts badly? It's got like really large error. This is technically not Gaussian. I mean, it's kind of Gaussian, but not. It's got a tail to one side. And it's not centered at 0. Why do you want it to be centered at 0? Because the majority of your errors should be what? 0, right? With a little bit to the left, a little bit to the right. Now, this is the process of a neural network learning. So you can see the little graph there. So look, let's wait for epoch 0. And you can see the epoch, and then the neural network, the weights are learning. And as it's learning, you can see that the error is being zero meaned and distributed around 0 and narrowing. Do you see that? And basically that the weights have learned by the time it gets to this, it's good and pretty stable. However, you may have nowadays a neural network that from the beginning and at the end, it'll end up like this. But actually, a neural network that does this from the beginning probably has bad weights. You know what I mean? And so you kind of want them to produce like an error that has a normal distribution. Okay. And so it is learning, obviously. It's definitely learning. And so but initially, I mean, a well-initialized network can look like this. Maybe wider and this is for a very easy data set, I should say. More complex data set might give you other results. Does that make sense? But I just want to illustrate at the end of the day, this is what we're doing. We're minimizing error. What was error? Defined as the y minus the y hat, right? So now I'm going to go back to that whiteboard. Go over here. Just grab that. Yeah. Where was that defined? Yeah, here. So when you do, so the error, the graph that you're looking at is actually a plot for error itself, which is y minus y hat. Remember, because we use NumPy or TensorFlow or things like that, we usually have a vector of errors, right? So we have a whole bunch of errors, but it's basically the real values minus the predicted values give you the errors. And then the thing that I plotted, obviously I want it to be zero mean, do that. And then we want to stretch that, like push that in. That's the ultimate objective. All right, so that's the perceptron. Hopefully that made sense. In the next, now we're just going to code it up. All right, so we're going to write the code and we're going to take this approach. And what's great about this is it's very incremental. So we're going to be doing the same thing as we start making the networks more and more complex. I do want to stress, though, that the change in the future will be that we need to more intelligently calculate this parameter. And this is what in 1986, those guys, Hinton and them, stochastic gradient descent, SGT, right? And you've used this optimizer. There's this one and the atom optimizer, right? Any questions? All right, great. So let's go ahead then and now go over code. So as you can see, that's the perceptron, pretty straightforward, right? All right, so let's now we're gonna need to start our Jupyter notebook. So I'm just gonna go just do this. Think lapse, right? Right there. So what I usually do in this sequence of neural nets is I mix it up, right? So I try to do things from scratch as much as possible. We can't always do everything from scratch. Like I have to hard code some things. And then obviously TensorFlow would calculate those things for us, right? And so we'll mix it up, TensorFlow and NumPy. But in this example, we're just pure NumPy, okay? All right, so let's go ahead and do conda environment list. Let me make sure I'm sharing. I may not be. I should. I think it's now there. All right, so yeah, so 537 should do it. Oh, my God. CDS. 2023. Okay, so here we are. Okay, so yeah, so you can see we did this dot product before. We're gonna kind of use that again, but we're just gonna build our code. So this will be the perceptron, basically. All right, so let's start the Jupyter notebook. All right, so we are going to create a new one. Let's rename it Perceptron. We should be able to finish this today. All right. And also what's so great about this is the same logic is kind of, or the approach is what you use in TensorFlow as you've seen. So it's going to be similar. All right. So except that we're doing the update manually in this case. Okay. So what are we going to need for this one? I believe in this environment, we've installed sklearn, right? We had installed it. All right. So we just need sklearn and we need NumPy, basically. All right. No TensorFlow today. We just want to what I want to do when I show you NumPy, pure NumPy, is to like make you see that, you know, we can decouple it from TensorFlow and still do a few things. So import NumPy as NP, and then also from sklearn dot model selection import train test split. And from sklearn, import data sets. We might use that or just build our own data sets. Okay, let's run this. Okay, good. Ran. Okay, so we are going to define some functions first. So we need a fit function. The fit function is basically where the learning is happening, right? So this is where the updates are going to happen. We have like the loop. There's always a loop. So I've said don't use loops, but we do use loops like when we're doing the training. It's got to happen. So in certain places. So we're going to look at some important concepts today. The activation function, we're going to define that, but you guys know the theory. You guys know how activation functions work. So activation function, right? Okay, so I'm just gonna put a return in all of these. Okay, so we've got an activation. I'm just kind of like laying out. We also want to have a function predict. So I'm trying to keep things like consistent with TensorFlow. Like there's a model, you fit it, you predict. All right, so it's kind of the same, similar idea. So define predict, right? Just gonna do return. Then we have accuracy. You guys, we've already defined this one. We can literally just use the same one. So define accuracy. Turn. Okay. All right. What else do we need? We're going to need basically to make some data. So we need our X and our Y. X comma Y. We're going to need that. We are going to need to split the data. So we're going to want to have, in a lot of the things that we're going to be doing most of the time from now on, at least in the neural network section, we're going to focus on supervised learning. So it's always going to be X train, X test, Y train, Y test. So we can almost always use train test split from sklearn to do this part. So I'm going to do X train, X train, X test, Y train, Y test, right? And then we'll fill in everything. Then what do we want to do? Once these things are defined, what do we want to do? We want to probably fit the model first. So just going to say fit now. We can always fill in. Once you fit it, I like to use things in like separate cells, just kind of a habit of mine. So, but yeah, let's do it like this. And then here, then we're going to say predict. Okay. Predict. So I'm just calling the previous functions. What else? Then once we have predict and all that, we call accuracy, right? Do the metrics. That's kind of the pipeline that we always follow. Okay. Okay, so now we can, some of these are very easy. So now let's think of the logic. Where do you want to start? We have a fit function. What needs to happen in the fit function? What do you think? Fit means what? Train. So training needs to happen in train. What does that mean? We need to find what? What does train give you? You were gonna say? The what?
Training with X.
With X, what? Yeah, and what do you need? But what's it like? We're creating the function, the inference function, right? That's what we're training for. So we need the weights. We need to learn the weights. It's all about the weights. I want to stress this. Have you guys heard of like transformers, right? Transformers, you can build the architecture right now. You can just copy literally what whomever did, build the architecture, but you still can't run it because you don't have the weights that took them massive amounts of everything to get. You see that? But if you can get their weights, like if you can go and get the weights of ChatGPT or whatever, you can replicate it. See, so it's all about the weights. You build architecture, you can build a lot of things, but the training gives you the weights, the weights and the biases, so the parameters. You guys see that? All right, so we're going to think it's always real because the weights are so important. It's always nice to decouple them. You know what I mean by that? So it's always nice to kind of treat them as a thing that you can carry around in your program, right? And you should do this as much as possible whenever you're doing TensorFlow, et cetera. Treat them as separate variables that you can move around, right? And the H5 file that you guys have seen before, it's kind of the same idea. You're saving the weights so that you can load them up again, okay? Very important. All right, so let's think about it. So let's start, I guess, with really fit is the most complex function, right? So fit is going to be the function that takes the longest to do. So we also need the data. So maybe let's start there, right? Getting the data. So this should be a lowercase y. Okay, so what data do I need? I'm going to I'm just going to create some data. So I'm going to use that datasets function that we brought up here, datasets, right? And that should be dot. It's got a nice module called make blobs. I'm going to invoke make blobs. And this will give me whatever I want. So I have to give it some parameters. So let's say I'm going to have 150 samples equal 150. So that's the number of data points that I'm going to create, but you can create more if you want. I'm going to say that I want features equal to 2. Okay? Like that. So this is now 150 by 2, correct? 150 by 2. That's it. Now you could initialize it like this randomly for sure. Okay, you could do that. Or you could initialize it by saying that it should come from a standard distribution. You see what I'm saying? So this data then has it's no longer random necessarily, but it's got more of a, like if you have a distribution, you're just grabbing things from the distribution, right? And it's kind of like that. It just gives it a little bit more structure. We could plot this or something, but it's not necessary. Right, so 150 by 2. So then we're just going to say that the data will have 2 centers, okay? And it's going 2 clusters basically with a standard deviation of 1.05. Okay. So cluster underscore standard deviation equal 1.05. And random state just means that because it's initialized randomly, that if you all want to replicate the same results as me, we can all have a seed value, right? So that's kind of what that means. So you can replicate. You guys see that? So hopefully this should give us our data. All right, and so we can, if I create a new cell here and move this one down, right? And so if I run this one, it should work. Yep. And then if I run x.shape, work, 150 by 2, right? If I do y, there you go. Okay, so it's kind of assigning the labels also for us. There's nothing special about it. We're just going to model this data, okay? Any questions? Guys, make sense? We can do the shape, y.shape, 150 by 1 column. So this creates our nice little data set. Now we can use this data set to train a perceptron. This is not the XOR problem, so it should be able to solve it. One thing you could do as practice is to run the XOR data on this, see how the performance does. You see what I'm saying? So what would you expect? Where would the score be, roughly? You did it with logistic regression, right? And it was like 70, I think, 75, no? 65. So you can, that's kind of a benchmark, right? And gives you some intuition as to what you might get, okay? All right, so this is important. So hopefully you're seeing how this connects to XOR. XOR is important because it's what Marvin Minsky used in their paper to kill perceptrons, right? They said perceptrons will not learn XOR. Killed neural networks. Even though they did say multi-layer perceptron, one hidden layer will solve it, but people misunderstood. So this is why I make such a big deal about this, right? So this is the perceptron. It was killed because of that paper. The paper addressed XOR operation, okay? Anyway, and then I've also stressed that it's not the activation alone, but one hidden layer and one activation. And then boom, you have a multi-layer perceptron and everything changes, okay? All right, and now you can solve XOR, and because of the universal approximation theorem, you can solve a lot. See all the pieces? All right, anyway, so now that we've done that, let's go ahead and do train, test, split. And this is just a standard thing that we've done before. So we give it X, comma, Y, and we give it a test size of, let's say, 0.2. And then random state, some value. Random state equal 1, 2, 3. See value. So now if I go ahead and do this, yeah, worked. So I've got my data ready to go. So what's the next thing I should do? What else do I need to do? Oh. So what do you think? So in the process, we need to have the weights and the biases initialized somewhere. And we need to, so we know that we need to fit the data, which basically means we need to train. So what data sets do we give it? We give it X train and we give it Y train, right? That's what we give it. When we give it this data to fit, it's going to learn, right? And if it learns, it basically now creates the model, which has the weights and the biases. So another way of thinking about this is that the output from this one is going to be the weights and the bias. And again, this is just a way of thinking about this as decoupled, right? Really what you want from fit is the weights and the biases, but you want them trained, not random. Once you have that, plug it into your predict function and boom, you've got it. You see that? So that's kind of what we're going to think about. So then predict down here should take the weights and the biases. And of course, it's going to take X test. You see that? So we've got X test, and then predict should give you, this is the convention that I usually do, is I call Y pred and Y real. I mean, you can use your own name, but I always try to be very consistent, so I always know what I'm looking at, right? So in this case, Y pred. Remember all of this, because we're using NumPy, is going to be vectors and not so much individual things, although it should work for individual things. But this is so nice to look at this way, because there's a thing called transfer learning. And in transfer learning, basically, this is what we're doing. We're just always sharing the results of our training. You can already do that with that H5, yeah. So like you could have, Brandon, you could have trained it and then, right, you give it to someone else or everyone, and you're sharing the model. This is the same thing, just like that, but more on a in the code basis. Any questions? Pretty easy, right? All right, so actually we're in pretty good shape. So we've got the data, we've got Y pred, what would come after that? Print the results, right? So then this is just print. You got this function already. What goes in here? Y-pred. What else?
Y-test.
Y-test, yes, good. So Y-test, remember, if we give it X-test, it's going to predict for this. Y-pred, we compare these to Y-test. Yeah, all right, so then Y-test. Here, we already have that one, and that one is this one. Okay, done. All right, and the accuracy function, you can literally just copy it from where we had it before. All right, so what else do we need? We need to figure out how to do the predict, maybe, right? And we need to have an activation function. We're going to stay to the standard activation function, which is the step function that I told you about, right? Only that it's going to be in the 0 to 1 shifting, not in the -1 to 1. Okay, so we can define that. Predict. Let's see if predict, we've seen this before, right? So let's go to the predict definition, should be here somewhere. Yeah, here it is. So predict takes X-test, right? X-test, comma, and then the weights and the bias, right? Right, takes that. All right, so how do we write this? What's going on here? This is the X vector times the weight vector plus the B, correct? Now, we've done this before. We wrote a couple of weeks ago or a week ago, I did something called the dot product function. And we did the for loop and everything. Do you remember that? Yeah, you have that code somewhere. It's intuitive that we wrote it that way, but you should never use for loops in that type of an approach, because if you were training a million records doing that, it would be very slow and frustrating, right? So instead, we always want to leverage NumPy or Torch or TensorFlow. So in this case, I'm going to do the part. So maybe I should write. I'm going to do, or no, I can just write it here. So I'm going to do the X times W part, the linear part, right? It's all linear, but this initial part, okay? So how can I achieve this? You should always think about how you can achieve this. So let's say the linear product and this one needs to take X test and multiply it times the weights, correct? Assuming they have the same dimensions, because you're learning, let's say 4 weights, or actually there's only 2 X's, so 2 weights. So we saw that code intuitively how it works, and I called it a dot product, right? That's what I said. That's, so I want to make sure you guys know what I'm talking about. Let me see if. GitHub, right? Then I believe I loaded this on the course. Do you guys remember if I loaded this? I can't remember. Sorry, I may not have loaded it. I guess I forgot. But well, no, the for loop that where I described the dot product at some point. I wanted to reference that, but I don't see it here. May not have loaded it. Sorry. You'll have to remember, but it was that operation that we did with the for loops. All right. So anyway, that operation, if I remember where it is, I'll reference back to it. But anyway, we're just doing the dot product, and NumPy has, long story short, NumPy has a function for it. That's what I'm trying to say, right? So all you have to do is np dot, but I just want you to know that what's happening here is that code that I wrote with those for loops, just that this is much more efficient and fast. And you should always do this. Okay, so this is the thing that's always going to trip you up in deep learning. That you will understand how to do something in for loops beautifully. It'll just be like very clear. But as the models get big, really big, you can't implement it like that. And so you have to always resort to a matrix multiplication. And you can do a lot with matrix multiplications. You just have to be very clever as to how you craft these things. And sometimes you will see these operations which look very hard to understand, but they're just matrix multiplications of things that are actually pretty easy to understand. But we just have to code it that way in order for it to be efficient. Am I making sense? So I want you to understand that, okay? And this is one example of this. I could have written this in a more intuitive way, but it would not be fast, and then it wouldn't perform, okay? And so that's sometimes the thing that keeps you from understanding a piece of code that you're looking at. It's a very common thing. This happens like in transformers. It's actually, the concept is simple, but you can't do it in for loops. You got to do it in some serious matrix multiplications that are hard to visualize. All right. Anyway, hope that makes sense. All right. So we're doing that dot product operation. It's probably in one of the videos. Just refer back to it. You'll see it. So now we just do this, and then we add the bias, right? And if you remember, so this just makes up our inference function, which is, imagine this is a vector. So W vector dot product X plus B. Got it? So right there, we just did the inference of the data. And then once we get that, this is like the Z value. Maybe I should have called it the Z value. And then now what's the next step according to what we discussed in the diagram? What do? We need Y pred, right? And Y pred is going to be equal to what? We already did that. That's what I'm saying, that we already did this whole operation, already took all the data, right? And so now all we want to do, we're doing, in case we have a batch, then we're doing 16 predictions. So if that's what you meant, then maybe you were right. But what I mean, if we get 16 inputs here, because this is a matrix multiplication, we're going to do all 16 times the weights, get 16, and then 16 outputs here, right? Remember, it's batches. This is tricky to understand sometimes, but if it's complicated, just think in terms of one. And then just think, oh yeah, but we do it for 16 at a time. But we need to learn, this is the predict, assuming we've got the weights and the biases, but we've got now, we go back to the whiteboard. What I'm saying is, yes, that's what I was getting at. So going back to the, here, right? X and W's, we learned the weights, we've got the X's, it gives us this, the Z, right? But what do we need? The activation function. So I said we're just using a step, but we could have changed it to a sigmoid end ReLU. Still, that does not make it a nonlinear universal approximator because it has no hidden layers, right? And this is why we started the perceptron, just to understand that concept. All right, so I'm going to switch back over here. All right, so then we need the activation. I conveniently already defined it up here, or I have a function at least. So I'm going to do Y pred equal activation function. And then what does it take? It takes the linear product. Could be any activation that we want, but we're just going to do the stepper function. All right, so I did linear output, and then what do we print out? Y pred. There we go. That's my prediction. Okay, the activation function then takes some value right? So what do we call it? Let's call it Z. Why not? And then we just need to return a function that is 0 or a 1. Right? So we're going to build. Now, we said that the label should be 0 or 1, right? So this is kind of the magic of neural nets, right? Is that we're going to tell it what the values are, right? And then we need to create like a machinery that can predict values within that range. And then by giving it examples, it's going to adjust the weights to predict those values. You see what I'm saying? It's like we kind of set what it should predict, and then it needs to learn to predict it, right? So in this case, I want it to predict values between 0 and 1. So I'm going to force it to predict 0 and 1, right? So it's going to predict any number, right? And so I can say, for instance, like an if statement. I need a condition, right? So let's just imagine if Z greater than or equal to 0, then I want it to be 1 value, right? So what would that 1? Else, I want it to be 0. Do you see that? It's kind of like that. And that's the stepper function, the shifted one, right? So if it's negative, 0. If it's positive, right? That's why the stepper function, it's called a stepper function. It's just like a step. I think we drew that somewhere in here. Maybe the other way around. Did I come?
Yeah, right. I just saw it when you're on pictures on GitHub.
Did I just use the pictures on GitHub? Oh, there we go. Last one. Right, so it's this, right? So you guys see, right? So if it's negative, 0. Second, it becomes positive, 1. That's what we're doing. Sounds complicated, but it's an if statement, right? And so let's go back to the code. But the beauty of this is we're forcing the model. You can only predict this, either 1 or 0. Make up your mind. You know what I mean? And so it updates the weights over time, and then eventually it gets it. I mean, surprisingly. All right, so then we're just going to use, again, a NumPy. We always want to use these because they're faster, always. So NP where, and TensorFlow has its own equivalents. And then once we do this, then we don't need the if. And then we can just do greater than or equal. So certainly greater than or equal. So that should mimic that stepper function behavior. Oh, yeah, it's the Z, actually. That's a good catch. Z, because it's the input to the function. Remember, we predict something. It's linear. It goes into this, which is non-linear, but that does it could no, this one is linear, but it could be a sigmoid, but that still does not allow the network to learn non-linear functions because it has no hidden layers. All right, that's the lesson there. That's it. That's the activation function. Okay. So we've got predict, we've got the activation function, the accuracy, you guys could pretty much set it up. We've got all of it here, except probably fit, right? So we want to, unless I'm missing something. No, that's kind of it. So hopefully you get it. So this is the equation, then it goes through the activation, that's stepping, and then it returns the predicted values, which can only be 0 or 1. So learn that, okay? So now we go to the fit function. This is where the majority of the work, or the heavy lifting, needs to happen. What's really amazing about this is that a lot of this will be very consistent with how we do deep learning, except that quite a bit goes into getting a better update, quite a bit. And that was stochastic gradient descent. That's what really made a big difference. All right, so what do we need to define here? What does fit take? What are the data? What does fit need? Not weights. Which one? For fit? But not with y tests and y.
Oh,
Well, okay, so you're thinking of more advanced, but we're at the perceptron, right? So so we have, yeah, I see what you're saying. So you want this to feed back in. We're not doing it that way right now, okay? So we're just gonna use X train and Y train. I see what you're saying. So we'll do it like that later. And so X train and Y train. Okay. That's it. We're gonna learn from this data. Okay. So what else do we need? So we've got X train and Y train. So where am I going with this? Maybe we need to go back to the whiteboard. Again, we're just implementing the perceptron, okay? Very like literally. That makes sense. So in the perceptron, I said this. We need to do this. And in particular, we need to do that. Right? So how are we going to approach this one? Okay, so we're doing everything here. All right, so let's go ahead. Let's start with the easy things, okay? We need to have some weights. We need to have a learning rate, which is this n value. So we can start to define these parameters. Let's go down. Oh, yeah, here. Okay, so we need then to define simple things like the learning rate. So what is that going to be? It's going to be some small value, usually between like 0.1 and 0.00001, somewhere around there. Okay, let's start with, this is important, 0.01. Okay, so we've got that. What else do we need? Let's do for, we're going to have a for loop, right? And this for loop is usually two for loops that we're always going to do here. So that's 1, 2, 3, 4. Again, why do we have two for loops? One for loop is going to be for what we call the epochs, and another for loop is going to be for the batches. And I'll tell you why. This concept actually took me a long time to understand. Like I don't know why I didn't get it for the longest time. But let's think of it this way. So for, you can do something like this, discard the value in range. And then this could be n epochs. Usually it's going to be coded as a variable, n epochs. But for now, I'm just going to do it as 1,000. I'm going to hard code it. And then the next one is going to be for, and let's say idx, comma, xi in enumerate x train. So what's happening here? You pretty much always do this. Doing transformers, you do this. Doing CNNs, you do this. You almost always do this. What are we doing? Who can tell me what we're doing here? We're obviously iterating 1,000 times. What's the second iteration doing? Goes through all train samples kind of individually, right? We're not going in batches. You should, in theory, go in batches because that, sometimes you need parallel computing. So you take advantage of giving 16 batches to the computer. You know what I mean? Like TensorFlow is made for GPUs, right? So if you have a GPU, you can give it 32 samples at once, do it. Okay, it's made for that. And so this is why most of the coding is always like this, right? We're going to keep it like that. So we give every single, here is only being done one sample at a time in this for loop. We give it the data. But then what is the meaning of the first for loop? What's the interpretation? So we are basically repeating this step here 1,000 times, right? And that's called the epochs. And that's a thing you do in machine learning. So basically what that means is this is the whole data set, and you give the whole data set to the model n epochs several times. Humans don't need that, right? So humans, you look at you fall down, you learn, right? Hopefully, right? So you get the data once, you view it, boom, you comprehend somehow magically. Deep learning does not work like that. K-fold was more for like, look, comparing performance multiple times and seeing it. Here we're only doing it. The train test split is only 20 to 80%. So we only do it once per se. But this is more like, again, going in deeper into how the models work. They're kind of not very smart in that sense that they need to look at the same data 1,000 times. So I get the whole data set and I need to see it again, and I need to see it again, and I need to see it again, right? 1,000 times. I don't know that I can say that, but maybe. I don't know. That you're interpreting what the network's doing. I have no idea. I don't pretend to know what it's doing. But what I can tell you, this concept to me was complicated. Why not just give it once, right? I would just think, okay, let's just go through it once, right? But no, you need to give it the data. And actually, one more thing, and this actually may be a very important thing that I'm not doing here is, every epoch, you should grab all the X train and do what? Shuffle it. And shuffle it. And that does make sense. Because when you give it, even though it's still the same train set every time, you're not showing it the test set, right? You're only showing it the train set. But every time it's getting it differently, like jumbled. And so it might look at it, and it's like saying it looks at it in a different perspective every time. You guys see that? So this is pretty standard. Although I'm not doing it as we go forward, we will start doing it, okay? Especially when it's a larger data set. So again, very important. You give it the epochs. Every epoch, you give it the whole data set. And in theory, you should randomize it every time. Like just randomize it and give it. Randomize it and give it. It's called shuffling. Does that make sense? Any questions? All right, so what do we need? The really important part, the really important thing that we need for the neural network are the parameters. What are they? The weights and the biases. These are usually initialized outside with the model, but here I'm kind of just doing it like this. So we need to initialize these. Initializing these, as I said, you should usually initialize them randomly, and you can randint or some kind of value and then multiplying it times something. But I'm just going to do zeros. In general, you don't do this in deep learning, right? You don't initialize all the weights to 0, okay? But here it's so straightforward. What's the size of this? It's going to be the size of X train. So we want to get n samples, so we get the dimensions. And we want to get n features. Okay, so we've got n samples and features. So we can get these parameters just by doing X shape. Everyone with me, guys? Is this making sense? Okay, great. So I've got n samples and features. So now tell me, how do I define zeros here? I need the dimension, right? So what's the value there? Is it n? Yeah, go ahead. Is it n sample? Is it n sample? And features. Yeah. Do you guys get it? Why? We're building a function that always takes how many features? 2. X1 and X2. That means we need a W1 and a W2. So 2. Do you see that? Okay. See, it's very mechanical, right? I almost think I can physically build this. I mean, it's so like mechanical. All right. So then we have the weights. Now the bias is just a value So that one can just be, I mean, we could do it very fancy, or you can just initialize its zeros, just a value, okay? All right, so we are there. What else do we need?
Variable bias, not bias.
Is it just bias? Okay. All right, great. All right, so you've got bias. Now comes the heart of this, the most amazing thing, okay, which is this part here. This is the actual learning, right? It would seem like maybe 1, 2, 3, 4, right? Indentation. So maybe before, when you've heard of neural networks, you assume it was like, who knows what, right? So bunch of calculations, you know, and it's actually pretty straightforward, right? So we need to, this always happens in TensorFlow, PyTorch, whatever. So what do? We need to predict, right? So we could call that predict function, or we can just copy this to make our code easy. So I'm gonna, I'm gonna do this. Okay, just like that. You see that? So what am I going to do? Do I have weights and biases? Yes. Here they are. You see that? Do I have X? Okay, so I'll need to change this, right? This needs to change. Do I need to perform a dot product operation? Yes, right? It should be the same operation. This gives me linear output. I think I have an error here. Let me double check my 1, 2, 3. All right. Pred, to get Y pred, linear output needs to do what? It needs to go through the activation. Do you see that it's the exact same thing? Maybe I'm not being very efficient with my coding here. Leave that to you guys to make it nicer and cleaner. But it's basically the same thing, except that instead of X test here, right, it's X train. But because we are iterating through the thing, right, what is it actually? What goes where the question marks are currently? Yes, X underscore I, right? Because I'm epochs, and then out of the train set, I'm grabbing one at a time and feeding it. Could I have grabbed batches from there? Yes, for sure. This is in fact how you will do it later. So I'm just letting you know now. It's bad practice to do it one at a time. Too slow. Because you give it one, it has to go through the whole gradient descent thing. Give it another one, has to go through all, where if you give it a batch, it'll do it in parallel, right? So you got, that's the thing. That's matrix multiplications that are happening to calculate those values, okay? So that you need to do it in parallel. Otherwise, you're just going to be waiting for a long time. All right, so then here we do xi. That's it. Okay, so now the model predicts, so you get the weight. Initially, the first iteration, the weights and the biases are terrible, right? So maybe the predictions are pretty bad, goes through the activation. But over time, as it learns, the weights and the biases need to improve. Do you guys see that? That's the insight right there. Okay, so now this is the part where it's very different, I should say, with stochastic gradient descent and deep neural networks. You need another approach. TensorFlow and PyTorch actually abstract this part pretty much so that we don't, instead of doing what we're going to do with the update, we don't actually have the update equation. We just do something called backprop and then step. It's like 2 calls, and that just does everything. But here we're doing it kind of manually. And so we need the update rule. So I'm just going to write a little comment here that says, now we need to compare. Now we need to compare predicted to real, right? Because we have a predicted here. Yes, Y pred. Do we have a real?
Y train.
To compare to Y pred. Not Y, not the, what did you say?
Y train.
Oh, well, yeah, Y train. No, you're right. Yeah, you're right. I was thinking white test. Yeah. No, you're right. Yes, exactly. These are the predicted labels, and we compare it to the real labels. Very good. Got it? All right, so we need to compare predicted to real. And this is going to be done here very specifically for the perceptron update rule. So in the 40s, they were already pretty close. They just didn't have like the great optimization that Hinton and their team created. And then that, that's much better. Okay, so now the update rule said the following, right? We basically said what? We go into we go to the whiteboard, right? And this was it, right? So we definitely want the learning rate multiplied times y minus y hat, so the real minus the predicted. And the perceptron had this, that it multiplied times, these values times the x. Okay, so we're going to do that, okay, just to see the effect. It's a weighing kind of a value, an additional one, but fixed to the values of x, okay? So let's go back here. Okay, so the update rule is going to be learning rate, right? Times what? Times y pred, right? Minus, and now what would we put here? We have all the data in, so this makes it a little bit tricky because we have all the samples in Y train, right? And we just need one sample, correct? So how do I solve that? Do I have something that I can conveniently use intentionally in there to make my life easier? We can use the index, right? Yes, exactly. So for now, and we'll wrap up here and finish this up on Thursday because it's almost time. But really, we are at the point where it would be what? Y train, right? You guys see what I'm saying? IDX. What is this IDX? This one. Enumerate is a great function. It's like, it makes your life so much easier because whenever you have a list of things, you can enumerate them, and then you get two things. You get the value and the index, and it just solves so much. You can see now we were getting the value, but then we needed the index to slice out from the train so that we can match apples to apples. Any questions so far, guys? Any questions? All right, so let's stop here for today. And then on Thursday, we will wrap it up. If you want, try to finish it on your own. That might be a good exercise, right? You're almost there. We're literally there, okay? And then think about it. Then we'll come and wrap it up, and then we'll do something with TensorFlow on Thursday. And, I'll give you a homework assignment or something. Got it? All right, great. So I'll stay for a few minutes if you have any questions. Otherwise, see you Thursday.